Hi, everyone. This video is a solution response to a request for number 5 from our Making Connections worksheet. That's section 3.5 from, I guess, our curriculum. The answer, as you know, is supposed to be never. But you will see that it's actually not never, but you're going to sort of argue and justify. So I wanted you to do this over homework so that you can wrestle with it. Number 5 is an incredible example of how math can be a really good model for things that we see in real life, but it will be very difficult to have an exact mathematical model to obey everything that we see in real life, especially in things like biology and even chemistry. No mathematical model is perfect, but it gets pretty darn close. Now, with the answer that we get, I will not technically not get the answer never, but logically speaking, you can sort of justify that it is never. So you might not be satisfied with that, but bear with me, hear me out, see the solution, see what it comes down to, and then you make the judgment for yourself. Okay. And you as students will probably going to wonder, is something like this what we're going to be prepared for the test? No, the questions and the test will be a lot more clear cut. Okay. Here we go. Question 5. The equation F models a bacteria count for tap water if you leave it to sit. So you could imagine the bacteria starts to grow. The equation G models bacteria of pond water that's left to sit. So you could imagine it's going to grow. And both models we test from t is greater than 0. Because, in science, typically, if you're doing an experiment, we're not going to go back in time. We could extrapolate, but we're not going to go back in time. We start from 0 and we start experimenting. Okay. So is the bacteria for tap water ever going to be bigger than the bacteria for pond water? Will it ever exceed? Well, figure it out and justify your answer. So remember, F and G, the Y values of these functions model bacteria count. The T models the time. So the question is, will the bacteria count, aka the Y value of F, ever be larger than the bacteria count, aka the Y value for G? And if I were to turn that into a mathematical inequality, the question that we need to solve is this. Without even solving it for now, that's where we are. And this is what you're tasked to do. If you got here, awesome. Let's get to it. As always, we are going to bring all rational functions to one side, not by multiplying the denominator, especially for inequalities, but by adding or subtracting the entire rational function, leaving the other side of the inequality as a 0. Whether it's left side or right side, bring them all to one of them, make the other side equal to a 0. Why is that? Well, in class, we talked about how there's potential to multiply by a negative, which means it changes the inequality, makes things very messy. We need to try multiple cases. It gets really, really complicated. So let's avoid all that. If we have this, all of a sudden, it should look familiar from all of the previous practice you've done. Your gut reaction should be to try and factor making the denominators common so that you can make a single rational function, single fraction out of them. Unfortunately, t squared plus 9 cannot be factored. So it's annoying, but you're going to have to multiply all of this by this denominator and 15t by that denominator. So excuse me while I get a little bit lazy, but the numerator will be 5t, t squared plus 9, minus 15t, t plus 2, and t plus 1. All over t plus 2, t plus 1, t squared plus 9. And there is nothing that we can simplify. Okay, so I am going to expand try to group like terms, see if I could simplify the numerator on its own, because again, from your practice, you know that if we have an inequality, we are going to end up with a interval chart. We need all vertical asymptotes, which means this, this, and this. We will need all x-intercepts, which will be all the stuff in the numerators that makes the numerator a 0. So everything has to be factored out. Let's do it. The denominator is going to be, the numerator is going to be, let's see, 5t cubed plus 45t. And let's see, t squared negative 15t cubed, 3t negative 45t squared, and 2 negative 30t, all over, excuse my shorthand, that's a bracket, bracket, bracket. Okay, I'm just lazy to write all that. That's the most annoying part, constantly repeating the denominator, leaving me with a numerator of negative 10t cubed minus 45t squared plus 15t all over t plus 2, t plus 1, t squared plus 9. Okay, that's not going to help me much, this numerator. I am going to focus on that, continue to factor out. I think I could factor out a negative 5 and a t, leaving me with positive 2t squared, a positive 9t, negative 3, all over t plus 2, t plus 1, t squared plus 9. All right, so negative 6, positive 9. I don't think that's factorable. So I'm going to test the discriminant for just the quadratic portion. That is b squared minus 4 times a times c. Oh, it looks like it does exist. 8, negative 3, positive 24. That is root 105, which means the zeros are going to be negative b plus minus root 105, all divided by 2a, which is a 4. And that's going to be 0.311 or negative 4.811. So those are the two zeros from the quadratic. We also have negative 5t, which means a 0, x of 0 is going to be another 0. We have vertical asymptotes of negative 2, negative 1, and that will never be a 0 because t squared equals negative 9. That means t has to be a root of negative values. That's not going to happen. So let's do the t chart and see if we can figure out when this entire function is going to be greater than 0. Okay, so I think I need more space. Let's bring it down a little bit. Okay, in order, we have negative 4.811, and then negative 2, and then negative 1, and then 0, and then 0.311, 0.311. I have negative 5t. I have the quadratic. I have t plus 2. I have t plus 1. I have t squared plus 9. And then I have the entire function. So because I have so many factors to test, I am actually going to do something slightly different for this. If you don't like what I'm doing, you don't have to copy it. Just do what you normally do. But I'm going to use a little bit of my own logic and what I know of quadratics to make my calculations really easy. See if you can follow. And that's a 0. Here we go. If I'm going to go left this time, instead of just going down in a column, I have a negative 5t. So if the t value is negative, I get a positive. If the t value is positive, I get a negative, which means that's a plus, that's a plus, that's a plus, that's a plus. And from here, as we use t values that are positive, that factor is going to be negative. Next, 2t squared plus 9t minus 3 is a parabola that has negative 4.8 and 0.31. And it's going to look something like this, which means if my x value or my t value is lower than negative 4.8, I'm going to be positive. If the t value that I use is bigger than 0.31, it's going to be positive. And all the x values underneath is going to be negative. See how simple that was? If you're not quite sure, go ahead and test numbers in between all of them. You'll get the same results as I do. The rest should be easy. T squared plus 9 will never be a negative. So this is always going to be plus. And I just have to worry about these two. Negative, negative, plus, 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 and negative, 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 plus, plus, plus. Here we go. That's a positive. That's a negative. That's a positive. That's a negative. That's a positive. And that's a negative. So when is this function positive, or rather greater than a 0? It would be here. Let's do it in a darker color. It would also be here. It would also be here. Remember, greater than 0, right? So it has to be here. Which of these are rejected? Well, if you remember from the original question, time starts at 0. We don't go back in time when we're doing this experiment. So if you see this, time has got to be greater than 0. And so we don't need this. We don't need to look at this. We don't need to look at this. And we don't need to look at this, right? Time is greater than 0. So my experiment starts from there. Now, when is the bacteria numbers in the tap water greater? Well, that is when this function is greater than 0, which means from 0 days to 0.311 days, the tap water has more bacteria than pond water. And that is where I'm just going to argue using logic, right? This is the only section, the very beginning of our, I guess, comparison of the two functions, is when the tap water has more bacteria than the pond. But I think we can argue that's probably not the case, right? Why? Tap water is fresh, whereas pond water has been sitting there for forever. So if you want to be technical about math, yes, as soon as we create pond water versus as soon as we create tap water, there is a, ooh, what is going on here? Something's wrong with my, something's lagging here. Let's see if I can close this program. But anyways, as you can see, if we had pond water that was like freshly created versus tap water that was freshly created, I guess we can make a comparison. But right now, that's not quite what we're doing here, right? We can imagine that pond water will always have more bacteria. I can't imagine feeling that pond water is safer to drink. Here's a comparison. I'm going to actually show up the Desmos. And there it is. Okay. From here to here is when you see the tap water having more bacteria, right? That little red line, right? The tap water has more bacteria than the pond water, and the pond water is safer to drink. But I hope you can take my argument that that's that's not quite what we would bank our safety and our health on. And so mathematically speaking, from 0 to 3 days, 0 to 0.3 days, the tap water has more bacteria. But realistically speaking, the pond water will always have bacteria. Okay, so if you haven't seen this video, you probably will be upset with me tomorrow, but just think about it. It's a question that I intentionally wanted you to wrestle with a little bit. It's a good example of how math models are not perfectly modeling real life scenarios, but it does do a pretty good job. Okay, hope that was good. See you tomorrow.